In this video, we will look at rolling a pair of dice, or actually simulating rolling a pair of dice. And there's also a version of this in the textbook starting on page 44. They take a slightly different approach than I'm going to take here, but it's very similar. So the key, at least our key for rolling a pair of dice, is actually rolling a single die. Rolling a single die. Because if we can do that, to roll a pair, we'll just do the same thing twice. So the key here is that when we do a roll, what we want to happen is we want the rolls to be uniformly distributed discretely between 1 and 6. In other words, we want all outcomes 1, 2, 3, 4, 5, 6 to be equally likely. So what we need to be able to do to simulate the roll of a die is to be able to sample from a discrete uniform distribution between the values of 1 and 6. For this video, we're going to do our simulation using Excel. And so Excel is a familiar tool, and Excel provides a function called RAND, R-A-N-D, that generates a continuously uniform random variable between 0 and 1. And so we have that method at our disposal. And so we can use the RAND function, which will generate uniform 0 and 1. And so essentially what we need to be able to do is convert one random variable that is uniformly distributed between 0 and 1 into another, which is discrete uniform. Let's just say between A plus 1, A plus 2, and B. So we need to be able to convert, because we know that we can use the RAND function to generate these U01. So we're going to call this U01, and we'll just call this one X, which is uniform discrete between the values of A and B. There are several different ways to do this, and if you're interested in how to do it or what the theory is behind the method we're going to use, we have a video dedicated to generating random variates. But for our purposes, we're interested in just creating the random variate. So we're going to use the following transformation. I'm going to assume that if I have a U value, I can transform that to X by taking the floor of A plus B plus 1 minus A times U, where this is the floor function. Essentially, we're going to round down because we're taking a continuous random variable and we're converting it to a discrete random variable. And so since our lower bound for our die, since we have 1 through 6, what we want to be able to do is 1 plus 6 times U. And luckily in Excel provides a function to do the floor function, which is just int. And so we can generate discrete random variables between 1 and 6 in Excel by just using the int function 1 plus 6 times rand, where rand gives us our U01. So now that we have our transformation, our formula for generating each individual roll, let's jump over into Excel and generate some rolls. So we know that we want to generate 2 rolls. Let's just call column A roll 1 and column B roll 2. And we'll just use the formula that we just developed. So it's integer, int, 1 plus 6 times rand. And then we're going to copy our roll from roll 1 to roll 2. And so you see every time I calculate in Excel, it recalculates, and so essentially it's resampling. So if I hit F9 to tell it to recalculate, I'm essentially resampling every time. And if I'm interested in the overall roll, I can just add the 2 rolls together and get my roll. And so every time I hit F9, I'm now simulating rolling this pair of dice. So let's copy this so that we can simulate multiple rolls. So I'm going to just copy just let's do 500 times. So I'm going to copy this down to 500. Let's see here. All the way down. I could use page down. That'd be too easy. So I'm just going to use the down arrow. 300, 400, down to 501 is going to give us 500 rolls. And so now we see that we have in column C simulated 500 rolls. And every time I hit F9, I'm essentially resimulating 500 rolls of my pair of dice. So before we continue and calculate the descriptive statistics that I'm interested in, it's worth asking at this point, how do we know that our model is correct? In other words, we're asking essentially the verification question here. How do I know that I've generated these random variates correctly? Well, in this case, we have a fairly straightforward way to check because we know something about each individual roll. We know that if we have a fair die, that each individual roll should be equally likely. So if I just do a frequency on the individual rolls, they should all be roughly equivalent. So let's do that. Let's just get our values. We know we have values 1, 2, 3, 4, 5, and 6. And what I'd like to know is if all of these values that I generated are equally likely, or if these 6 values are equally likely from what I generated. So what we're going to do is we're just going to use the Excel's built-in frequency function to calculate that. So we will do equal frequency, and we want to do all of the values between A2 and B501. Those are all of our individual rolls. And for our bins, we want values 1 through 6. And so we do Control-Shift to get our counts. And so now we have the frequency, or the count, for these individual values. So let's label this count, but what we really want is the frequency. So we'll simply take the count values and divide by 1,000, because over both die we have 1,000 rolls. And what we expect to see, oops, don't want to do that. Let's go back to the home here. I want to copy this value into these other cells. And so now all of these values should be the same. And so when I resample, I'm comparing the frequencies that I see here with my expectation, and my expectation is that each one of these should be 1/6 or 0.1667. And so I'm going to continue to hit F9 and just watch those individual values until I'm satisfied that they are the same statistically and they are centered around 0.1667. Of course, as we know, if we're not satisfied, if I continue to hit F9 and I'm not satisfied that those are equally likely, I can always increase the number. So instead of doing 500, I could do 1,000 or 2,000 or 10,000 or 50,000 until I become satisfied. But for now, let's just assume that these values are close enough so that we're satisfied that these values are correct. So now that I have that, I can collect the information that I'm interested in about my roll values, which I know less about. So again, I know that my individual rolls, values 1 through 6, are equally likely. For my rolling the pair, I have less information. So let's just look at the sample average and sample standard deviation for our values. So let me get this and look at these values associated with our response here in column C. So let's just use the Excel functions here. Average of C2 to C501. And standard deviation, C2, C501. And we can then, again, resample by hitting F9. And we see that our sample average looks to be somewhere around 7, which should be within our expectation, again, because of the equally likeliness of the individual rolls. Similarly, we could do a frequency, use the frequency function to see the frequency of individual rolls. We know that the rolls, when we roll a pair between 2 and 12, we can't roll a 1 because we have 2 dice that have to be rolled. And so we'll use the same thing, the same method that we used for the individual dice, except we will use the roll, the sum column. So we'll use the frequency column C2 to C501, and our bins are 2 through 12. Compute the frequency, hit F9, and then as we did before, we will compute the frequency, but this time we don't have 1,000 observations because we're getting the sum. We have 500 observations. So we'll get our 500 observations here. And just to make this look consistent, let's make sure that we have the same number of digits to the right of the decimal point. And so we can again F9, F9, F9 to do a resampling. And we can see what we should have expected along the way is that the 7 is the highest frequency, and then the distribution is symmetric around the 7, hence the sample average of 7. So summarizing what we did in rolling our pair of die, we recognized that we could simulate, or the key to simulating rolling the pair of dice was that we needed to be able to sample rolling a single die, and that rolling a single die was equivalent to generating a uniformly distributed random variate between 1 and 6, a discrete random variate, and that we could do that by using the XLRAN function, which generates a continuous uniform random variate between 0 and 1, and using the transform that we developed. We then replicated our roll 500 times. We then used a frequency to do our initial verification, because we know that if we look at all of the rolls, each one of the 6 outcomes should be equally likely. And once we were satisfied that that was the case, we then computed the descriptive statistics that we're interested in. In other words, the average and standard deviation of our roll value. And then we similarly did a frequency for our values, the values of our combined roll, which are between 2 and 12.